If you ask 100 ham radio operators out there in the wild on how to build an half-wave end-fed antenna resonant on 10 and 15 meters, most of them probably will tell you to get 20 meters of wire, attach it to a 1-49 transformer, and tune it. But that essentially would mean that you're going for sort of a classic end-fed for the 40 meter band, which then is resonant on 7, 14, 21, and 28 megahertz, at least if you tune it right. Now, what if you don't want to have 7 and 14 megahertz, but you really only want to have 21 and 28 megahertz? For example, because you're a ham radio operator in Germany with the Class E license, which doesn't allow you to transmit in 7 and 14 megahertz. I was wondering, there's got to be a better way to do this. If you don't want to carry 20 meters of wire, which mostly half of it is dead weight because you're not going to use it for 7 or 14 megahertz, then the answer might be a trapped end-fed for 10 and 15 meters. Interested? Then stay tuned. So, what do we need for the so-called trapped end-fed half-wave for 10 and 15 meters? We also start with a 1-49 transformer. We always need that. We add about 5 meters of wire to get at a 10 meter version first. We then attach a PCB trap, and I'm going to get into that in a few minutes. And then we need a bit more wire, 1.5, whatever, wire, to accommodate for the 15 meter band, and then we land with a trapped end-fed that is only resonant on 21 and 28 megahertz at a significantly shorter length. And here we go. So that's the do-it-yourself kit for the 1-49 transformer that I'm gonna use for the basically 10 meter end-fed, and then we're gonna extend it, but I'll get to that in a minute. No real issues there. I built a few in the past. I specifically choose a bit of a smaller one, but I'd still like to use one of these PL sockets instead of the BM that's in there somewhere. So that might be a bit of an issue because it's going to be a bit tight to get that in there, but I'm pretty sure it's still going to work. So that's that. And then we have the way more interesting do-it-yourself kit for the trap. It's a PCB trap. So basically, in case you're not familiar with the concept here, this is basically going to be the capacitor, and you see there's actually marks in there. So you can actually adjust the capacity it will have. In my case, I want to build it for 10 meters, so I'm going to cut the metal part here. It's basically a metal plate on top and on bottom side, so that's going to form the capacitor. We're going to cut it on the 10 meter mark on both sides, so it's going to be way smaller than the whole part, and that's going to limit the capacity there. And then we're going to do sort of a coil around it, so that should basically fit in there, which provides the inductivity, and that together should ideally block 28 megahertz. No real experience on those, so that's going to be interesting. I built a coax trap once that doesn't really work, but I didn't have a nano VNA back then. I do have today, so I'm really going to measure this through to make sure it really blocks the frequency that I need it to block. So yeah, that's going to be the fun part. So first part is going to be build the 1-49 transformer, attach about 5 meters of wire to basically build the 10 meter end-fed half wave. And then we're gonna build in a second step the PCB trap, attach it to the 10 meter end fed, add another, I don't know, 2 meters, 1.5 meters. We'll have to test that. And that together combined should essentially build the 10 and 50 meter trapped end fed half wave. I'm really curious to see if that works as expected. Follow along. Okay, so I have the 10 meter end fed ready now. So we have the 1 to 49 transformer, quite a small form factor. It was a bit hard to get the PL plug in there, so I had to cut the like 2-3 millimeters on the top, but that's totally fine. About 5 meters of wire. I initially planned to use this more like the stronger, I don't know, steel, isolated steel, whatever wire thing, because it's quite strong, but it's actually meant for gardening when you want to provide a hold for bushes or whatever, but it's not as flexible. I actually used it for one of the end feds I have, and I like that it's so strong. It can really pull hard on it, but it's not very flexible. So in this case, I went with a more common copper, isolated copper, whatever thing. I think that's gonna be better here. So that's done. I tuned it to 28.2 megahertz, and I didn't really think about what I would tune it to. But yeah, the reality is I'm going to use it primarily for FT8, which would be 28.074, and then also a bit SSP voice that would be up to 28.5.6, whatever. So somewhere in the middle. It's obviously you'd compromise on both ends then, but I think yeah, that should be fine. A few kilohertz left or right should be fine. And then also I'm not entirely sure when I add the trap that's not gonna change, at least to a small degree, the tune frequency, so like the SWR. So I'm gonna go for that for now, and then I can still adjust at least to a certain degree whether I want to tune it again. Now to the more interesting part here, and I think I mentioned it already. I've never built a trap before, so it's really going to be the interesting part. I'm going to turn towards that now. But before doing so, I really wanted to, yeah, just to double check, sanity check, if you will, the capacity. So basically, what you see, like the lighter blue, is sort of a metal, and both together form the capacitor. And then the idea is that you cut through the lines as you need. In the beginning, I thought, like, why not use the complete one, and then there's a neat formula to calculate the trap, and that's primarily the inductivity of the coil and then the capacity of the capacitor. So I was like, why not use the whole thing, and then just adjust the windings of the coil, so the inductivity. But then I was reading somewhere that that will affect quality, so that's what we don't really want to do. And then again, I've never built one, so that's probably not the place to start experimenting. So I'm just going to follow common knowledge, or like the instruction that comes with it, and cut through the lines for the 10 meter band, because that's what we want to block frequency wise. But before doing so, actually, I just wanted to measure the capacity in that state and form. So you can do that in two ways, obviously. Probably even a few more that I'm not aware of. One is you use an LCR meter, so that's a rather, let's call it, affordable one. I'd not say cheap. It worked quite fine, so I don't want to be disrespectful here. It's a nice device. It does what it's meant to do, but it's rather affordable. It's a nice one. Or you can use a nano VNA. But yeah, nano VNA is a bit more fiddly, right? You have to calibrate and then make sure connect everything correct. So maybe I do that as well. But for the soul capacity, the LCR meter should be more than enough. Just yeah, basically really just as a sanity check from the instructions or like description. The capacitor should have, in its current form, it should have a capacity of 49 picofarad, I think it is. So if we measure it right now, so you see we are 1-digit nanofarad. So, and I'm not gonna tell you I didn't try it before. So yeah, you see it's moving already. So that's just the device itself. So I mean, it's always gonna be a bit not super specific, but you see it's fairly close, right? 0.047. It should be 0.049. Oh, you can't actually see it, apologies. So we're at 0.04748. That's perfectly fine. It should be 0.049. So that's totally fine. Maybe I'll also just double check with the nano VNA, although it's a bit more fiddly, let's see. But that's a good start. That's very close and probably just within the limits of what this device can do. So I know now that the measurement I do is correct. The capacitor seems to be fine. So now we're gonna cut through those dotted lines for the 10 meter band and measure again. Okay, so what I did just now is, like, this might be a bit overblown, but it's actually the fastest way to cut through it. Just basically cutting through, here we are, through the metal part here. Obviously you don't have to cut a hole in there, right? It's really enough to cut the metal part on both sides so that the capacitor or capacity is smaller then. And then once again measuring, we should be at about 12 picofarad. Now let's see, I don't want to block the view again. And what you should be seeing, and again I did test already, of course, we are at 0.10, so there's a bit of an inaccuracy here. But that is super fine. 0.11 or like 0.010, 0.011. That's pretty damn close to the 0.012 that we would actually like to see there, according to the description. But all in all, knowing that, it's totally fine. I'd probably use the 0.011, like the 11 picofarad, for calculating the coil. And then obviously there's still ways to tune the trap itself. So not the cleanest cut, but I mean, you won't see it afterwards anymore. But the more important part is we're ready to build the coil. Capacity is down to 12, 11, 10, whatever picofarad. So now we're cutting a line here and here so that it sits basically somewhere here. And then we put the copper wire around it. I'll have to calculate actually how many windings I need. And then, yeah, we're almost there. We're soldering the copper wire here, antenna wire goes there, and that's basically just to hold the trap itself. And then at the end, there's shrink tube to hold everything together. I was reading quite a bit on
how to avoid moisture, humidity. Gotta think about that. Some people use like, I don't know, plastic spray or whatever. It's I don't know. I'll have to think about that. But let's do the coil first. Measure it again, just to for the sake of doing so, and then once that is on the trap or on the capacity, we have the trap, and then we can measure the trap itself. But for that, we do actually need the nano VNA then. So that's gonna come in later. All right, so this is the first try of building the trap. And it failed, I have to say right from the start. I'll tell you in a second why. The main issue actually is that it's extremely hard to put the windings on there in a way that you could still adjust them. It's almost like a binary thing, right? Either they stick where they are, but then you can't really fiddle with them anymore to, basically adjust the inductivity, or they are so loose that they just don't hold on it. Like it's, and then you also can't adjust it because they will just float around. So I just decided to hot glue them, knowing that this is not really a permanent solution, but this would basically put them at the place where they should be, assuming that the inductivity would be, like after measuring it with the LCR meter, assuming it would be the right inductivity anyways, and then soldering it. But then when measuring, and I'll show you a picture here, while measuring through the nano VNA, the thing is that, yes, it's working, so that's the positive thing here. The dip, or more like the curve, is I think at around 31 megahertz. So we're currently blocking 31 megahertz. And that's not where we wanted to block, but that's not the big issue. We just need to increase inductivity, I think. So I'll just add 1 or 2 more windings. I'll probably just start with 2. But the bigger issue actually is that it's not a sharp dip, right? It's quite a slow curve, if you want. So that means, as far as I understand, that the quality of the trap isn't good. Otherwise, it would be a sharp dip. And currently, in the current state, even if we would bring the frequency down to 28 whatever megahertz, it wouldn't be really usable because we would block even 21 megahertz that we want to use as an extension to the trap after the trap. Even that frequency we would block significantly, so we wouldn't really be successful with that antenna. So we need to increase the quality of the coil, I would say, because the trap itself, I mean the capacitor itself, what else can we do? But the trap is, and you can see it's crappy. It's a crap trap, if you will. So that needs to go. That needs to be shorter. But then also I had to rewind a few times, so there's a few edges in the wire as well. So I'll turn towards a completely new wire, add 2 more windings, solder it together to the PCB board again, like here. Whoops. And then I just put the screws in there for easier measurement. And then, yeah, I'll just measure again. I really don't see how I would be able to put the windings on there, solder it without fixating the wires, the windings in any way, so that I could still tune the trap while it is soldered. I don't know how people do that. I'll just give it another try, hoping I would come close to the 28 megahertz with 2 additional wire windings. And I don't know, man, just take it from there. Let's just see how that works. Alright, so this is version 2, and I just randomly added 2 windings without calculating, just trial and error from this point onwards, I would say. But as you can see, that's a perfect fit on frequency. So we have minus 42 close to 43 decibel that are being blocked here at 28.4 megahertz. So that's super fine, but still, when you go up to 21, we still have about 14 decibel, and that's just way too much. Way too much. There's no way you could, actively be on air with a feed with minus 14 decibel here. So yeah, I don't know. I don't really know how to make this any better. You can see that you can actually, I managed to get the windings on and still being able to tinker with it to tune it. So I'm totally mistuning it right now, but it doesn't really matter. It's just for the sake of showcasing how you can actually do that. We should probably still be around 28, whatever. So yeah, I don't really know what else to try to improve the quality. It's somewhat fine, all the windings and stuff, but it might also be the correlation between the capacity and inductivity, although I think that should be a nice relationship between those anyways. So I'm a bit clueless, but what I'm gonna do, I want to keep going, I want to be in action. What I want to do is just connect it to the EFHW, to the rest. So it's not much efforts from here onward. I'm not gonna put the heat tube on it. I'll wait for sunny weather, and then I'll just attach it to the EFHW I have for the 10 meter, and put around 1.5 meter or so, close to 2 meters behind the trap, and I'll just see if I can see a resonant 15 meter part. All the test environment here with all the cables and metal parts and whatnot, and also the measuring cables might not be ideal, they're not shielded in any way or whatever. It's just gonna be a test. I'm not super convinced that it will change, but maybe I get a surprise. But I guess I'm not gonna see a 15 meter resonant part behind it. But yeah, I'll just try. Let's see what happens. So here we are back at my workbench, and what a surprise, I can tell you. But let me just run through the setup. So you remembered I just wanted to see the trap on air, like how it behaves when it's actually put into some wires. So we have the 1-49 transformer here going through about 5 meters of wire for the 10 meter part going into the trap, and then from the trap another piece of wire, super short, doesn't feel right, but we'll get to that in a second, for the 50 meter part. And you might remember I just wanted to see how the trap behaves in between wires, because measuring is one thing. And I was super surprised to see not only the dip on the NanoVNA when I was measuring SWR, not only the dip for 10 meters, but also a clear dip at 19 megahertz. That's just what I got when I attached some wires, like 1.5 meter, whatever it was. So I was like, whoa, how come, right? Because the trap didn't seem to be any good when looking at the NanoVNA. But I have to say, somehow I probably just messed up the measurement with the NanoVNA, because there is a clear dip, and then I was like, you know what? Let me just tinker with the second wire and see if the dip moves. And it's also a very sharp dip. It's totally fine. And it actually did move. So it took me a while because, as you see, the wire after the trap is super, super short. It's like, I don't know, 40 centimeters. It can't really, I can't digest in my head how come that it's just so short. So I had a hard time. I had to shorten because it was going super tiny bits because it's just so short anyways already. But in the end, I ended up with like 21 megahertz. That's this picture, right? So yeah, that's it. The measurement of the trap obviously wasn't correct on the NanoVNA because I thought like with minus 14 decibel, whatever it was, anything after the trap would be dead weight, right? That wouldn't make any difference, but it does. So the dip for the 10 meters stayed exactly where it was. That's fine. And then the dip after the trap did move. So it's just a matter of tuning it to the right frequency then. And now I'm actually, yeah, that's what I wanted to build. We have an end-fed half wave for 10 meter, and then the trap, and then another very short piece of wire, but resonant on 50 meters. So that's it. It does actually work. And that's super surprising, but also very pleasing to see. It's done, basically. So obviously there is a few more things to be done. I need to put the shrink tube on here to give at least some sort of protection. You can see from the second picture also that the SWR, like the 10 meter part is resonant at, I think it was like 29 whatever megahertz, so that's a bit too high. So I have a bit of wire left here. I need to tune it a bit more. I was somehow expecting this to be a bit different when you're up, like it was just 3 meters, and that's also why all the wires are a bit shorter than I would have, or like way shorter than I would have expected, because I was tuning quite near to the ground. But then, I mean, this is yeah, thought to be for portable operations, or more like when I'm on holiday, I just grab this one and can be on air for 10 and 50 meters. But at home, you can see what the best point is to get it up to. When you're traveling, when you're in a hotel or an apartment, you might have a garden, you may have just a balcony. You don't really control the environment, so I would expect it to be used lower, near to the ground anyway, so I was tuning it there. So let's just see. But that obviously does affect the length of the wire as well. So I would still tune the 10 meter part to get it down to like 28 megahertz, and then see about the 15 meter part again. So far it looks quite okay. I think if I remember correctly, it was like 21.5 megahertz or so, which would be fine. But it could be that when I tinker with the 10 meter part, I will have to fine tune the 15 meter part as well. Let's see. But yeah. Anyways, I don't know. That's it. It's done. It works. I'll spare you the rest. The rest is just basic fine tuning and stuff. So man, I can't tell you how happy I am that it actually works. It was quite a hard way to get there. And yeah, I was ready to completely redo the whole trap. So I'm really happy that I just tried it. And yeah, SWR reading is one thing. So I'm gonna hook it up. I'm getting the shrink tube on it, and then I'm just gonna hook it up to my 991A probably, and see how good and easy and far away contacts I can make. But as far as it goes for this video, I'd say we're all done. We made it. That's the end-fed that I wanted to build. Now it's time to actually put it to some real-world tests. And thanks for watching all through this video. Hope you enjoyed it. Get out there, get dirty, get stuff done. 73 from Delta Oscar 7, Delta Tango Lima.